Okay. Good morning. The answer keys for homework assignment 2 should be going around. If you can pass the homework assignment to somewhere up front, that'll be good. So how is the homework program number 2 coming along, the programming project? Okay. So if you run into any problem with actual implementation, let me know soon, and we can just get started this weekend. Right? So before we move on to the next topic, was the stuff that we did last class or the stuff before, was that clearer when you went back to think about it, the notion of serializable and all those things, right? I suspected that people who took databases should have had that part. So if you, it's basically database concept. So I'm not going to spend too much more time on it because it's mostly a database concept. We're just giving a very high-level view of that. Like, if you have more questions about that, we can go over them in class right now, or we can talk in the office hours. So was that kind of okay? Okay, so let's move on to the next topic in this module, which is the notion of deadlock. We kind of talked about it before. We said, that there's a possibility that processes can get into a state where nobody can make progress, and you can be in this deadlock state. So we're going to look at what this deadlock is, what conditions have to be, what have to hold for deadlocks to happen, and what you can do about it. Either can you prevent deadlocks from happening, or you can avoid deadlocks completely, right? And most operating systems that you will use don't do anything about deadlocks. Windows or Unix versions don't do anything about deadlock. They assume that deadlocks don't happen. If they happen, they happen rarely, and you would recover from them in an undefined fashion, like maybe kill the processes, right? But we'll see what would be required for a deadlock prevention or avoidance algorithm to work, right? So, the notion of deadlock is basically when things cannot make progress. So, if you look at it, so if you're holding a resource and the resource cannot be taken away from you, and you want another resource, right? If there are two processes doing the same thing, if they want each other's resource, then you end up in a deadlock situation. And that can happen for resources which cannot be preempted. For example, a tape drive or a printer, right? If I'm printing half of my document, I cannot preempt my process, give the printer to somebody else, and have a useful output. Printers are exclusive devices. So till my printout is fully done, you cannot interleave two printouts on the same time, right? Tape drives are the same thing. You cannot burn a DVD, or you cannot take a backup halfway through, switch out to the other process, and come back and finish these processes. So when you have those kind of stuff, and so if I have a tape unit and I want a printer or something, then you get into a notion of a deadlock. We'll see in the next slide what conditions have to hold. The other case is if you're using a semaphore where there are two semaphores, one process needs, has one thread, has one semaphore, wants the other, and the other process does the opposite. So they both get into a deadlock because they can't proceed to release the semaphore, right? So they're both waiting for the other one to finish, and till one of them finishes, you can't make progress. Right? So So we have a notion of resources. So you have a notion of resources and classes. So you can say there are certain number of printers on a machine. So resources, you name them as R1 through Rm. And resources can be memory or CPU or any of the resources that the operating system would manage. And you may have different instances of the same resource. So printer, you may have different printers. Each one of them can do the same jobs as you want. And so the way you use them is you request this resource, you use them for a while, and then you release them. Right? That's how you tend to use resources in operating systems. So for deadlock to happen, 4 conditions have to simultaneously hold. Right? All of them have to hold. If all of them hold, then you are in deadlock situation. So the first one is mutual exclusion, right? So the resource that you're talking about, only one of them can use at the same time. So if many users can use the same resource at the same time, then deadlocks cannot happen, right? So then we were kind of talking about the same notion in a more informal fashion before. I hold some resource and I want something else. If the resource can be shared, then there is no deadlock. So you need to have resources which hold the mutual exclusion property, right? You need to have a hold and wait. So if I have a resource and I'm waiting for another resource, so I need to hold something before deadlock happen, right? Deadlock cannot happen if I have no resources at all. Deadlock, for deadlock to happen, I need to hold a resource, and that resource will need the mutual exclusion principle. So I need to hold a resource which somebody else has to want, and they can't get it till I give it back. So I'm holding a resource which, till I give it back, nobody can take it, and that's the no preemption principle, right? So I hold a resource that no one else can share, and no one else can take it away from me. So unless I give it back, system cannot preempt and take it away from me, right? So stuff like printers are non-preemptible. I can't take the printer halfway through and give it to somebody else. Stuff like resources like CPU are preemptible, right? So I can't get into a deadlock with the CPU resource because we looked at how you can do a preemption. You save all the state and then you can bring it back. So if I'm holding a CPU, which only one process can use at any one time, and I'm holding it, I'm looking for another resource, right? But CPUs can be preempted and brought back to the same state. So the third condition won't hold for CPU resources. And the last one is there has to exist some way to have a circular wait. Right? One has to wait for another one, another one has to wait for another one. So it may involve one process or multiple processes. The previous example in semaphore included 2 processes, but in general case it can include multiple processes. Right? So one process may have resource 1, wants resource 2, second process may have resource 2, wants resource 3, and so on. But eventually there has to be a circle, right? So there's a circular wait, so all of them have to hold. If one of them doesn't hold, then deadlock cannot happen, right? So this is basically the notion that we talked about in a more formal fashion. So in order to understand how the deadlocks and all work, we introduced the notion of a resource allocation graph, right? So we graphically try to show the state of the different processes and the state of the different resources. So we define resources by R1 through Rm in the system, and we define processes by P1 to PM. And we represent processes with the circle and the resources with the square, right? It's not important how you represent them. And resources can have many instances of the same thing. So a printer can have more than one printer hooked up to a same machine. The way we define edges is if there's edge from a process to a request, that means process is requesting a resource. And the edge from resource to a process states that that resource was assigned to this process. So for example, this is how you may have a resource allocation graph, right? So the gray square boxes are resources, and the number of dots inside says how many instances of that particular stuff there is. So for example, R4, there are 3 of them. R2, there are 2 of them. So if you think of resources as say printer, there are 2 printers in this particular machine, right? And we assume that both of them can be assigned to different processes. They're not different, so we don't care about which printer or which instant of the resource. Any one of them is fine. So in this graph, R2 is assigned to, one instance of R2 is assigned to process P1, and P1 waits for R1, right? And R1 is assigned, one instance of R1, which is all there is, was assigned to P2, and P2 is waiting for R3, whereas R3 is assigned to P3, right? This is a way to represent the state of the system. It shows the number of resources, what was assigned to what, and what is waiting for what. So resource R4 was not assigned to anybody, and P3 is not requesting any resource. And we can use that to look in the system to figure out when a deadlock happens, right? So we changed the graph we had before to have P3 request the resource R2, right? And now this gets into a deadlock, and we can see why this gets into a deadlock, right? So there are two instances of R2. So if it is possible for any one of R2 can be assigned to one. So there are, if you look at the graph, there are two circular weights, right? There's a circle going from R2 to P1 to R1 to P2, and actually it goes back from P2 to R3 to P3 to R2, right? If you follow the arrows, it goes around like that, right? And you can see why, even though you have two resources of R2, you cannot break this deadlock, right? Because R2, so P1 holds one of it, and if it follows the second no preemption, the third no preemption policy, you can't take it away. So P1 has R2, it's holding to it, and then it's waiting for R1, right? R1 is assigned to P2, right? And P2 also wants R2, right? So P1, if it got the resource R1, hopefully it can finish and release the R2, which will make P2 make progress. But that is waiting for the second R2, right? And there's a loop here. The P2 is waiting for R3, R3 is waiting for P3, and so on, right? So you can pictorially describe what the state of the system is, what resources are being asked by whom, and follow these things to figure out that there is a circular weight and that it cannot be solved, right? So does that make sense to look at the graph? So if you look at this, it's not that easy to see if there's a deadlock, right? See, by just looking at this R2, P2, R3, P3, right? There is a deadlock, but that's not the reason why there's a deadlock. It has to be the other one, because there are two resources. So if any one of them would solve the notion of where the deadlock happened, then you can get out of it, right? If the second half did not exist, then there'll be no deadlock because there are two resources, right? So the notion of finding out whether there's a system is in a deadlock or what is not trivial. I hope just by looking at this, it's obvious that it's not trivial, right? And that's the reason why typical operating systems don't do that, because finding out whether somebody is in a deadlock, it's a little easier if you draw all this graph like this and then you follow these things and then figure out what's happening. But for an operating system to make decisions on the fly, it's not a trivial task, because there's no resource graph like this built in, right? And so this is another different resource graph, and there are no cycles and no deadlock, right? There is a, if you follow the arrows, there is a cycle, right? But there are two instances of R2 and R1, and so they could potentially come back, be returned, and have the system go through, right? So the notion of deadlock does not address the notion of starvation. It does not say how long you have to wait to get the solution. So this particular graph may have starvation, but it's deadlock proof, right? And deadlock means that there's no way you can possibly make progress. The starvation means that there is some way, right? And that way may take you forever, but there is still a way to break the stuff, right? Is that clear? So basically, this is what we looked at. So if the graph has no cycles, then there is no deadlock. But if it has cycles, then you have to see where the cycle happens. If the resources, there are multiple instances of the resources, then there is a possibility of deadlock depending on what happens. So that's what you saw in the two graphs prior to this one. But if there's only one instance which is part of this loop, then you get into a deadlock. So depending on how many resources there are, you may either get into deadlock or not by looking at the resource allocation graph, right? So this is what we're talking about here. So if there's only one instance of R2, you only need the R2, P2, R3, P3 to say whether there's a deadlock. If there are two instances, you need two of these. Right? So depending on what situation is, you can look at the graph to say whether there's deadlock or not easily. Right? So when you write programs using semaphores or locks and stuff, unless you are careful, you will get into a deadlock situation, right? Either in the user code or even the kernel when it's just doing locking and stuff, you can get into a deadlock situation, right? Deadlocks, when deadlocks happen, usually there's very little you can do, right? Because by definition, the resources cannot be preempted, so you can't take the resources away from any one of the processes, and they're all waiting to make. So there's nothing the system can do to break the deadlock within themselves. So usually what you can do is you can kill the processes, right? So if you're halfway through a printout, I can kill the process and restart the processes. There is no easy or good way to continue from a deadlock, right? Because the resource that you're holding is mutual exclusion principle. So the system cannot resolve the deadlocks in a nice fashion, right? So there are three ways to react to deadlock in a program. One is to make sure that you will never ever get into a deadlock state, right? And that's deadlock avoidance. So make sure that deadlock can never happen, right? So the notion here is there is no possible condition that you can get into a deadlock, so you're extremely conservative on what you would let you do. You can prevent deadlock, which is in all likelihood you won't get into deadlock and you can make progress. Or the other approach is pretend deadlocks don't exist, or if deadlock happens, the OS is not going to do anything, and it's up to the users to deal with that, right? And that's the approach taken by most of these systems that, like I said, that you use. Windows or Unix don't deal with deadlocks. If you have a code which gets into a deadlock, it just stays in deadlock, and you probably have to try to kill the processes or reboot or what have you, right? The assumption is deadlock doesn't happen often, so it's kind of okay. Yes.
Is that what you mean by recover? Like kill the processes or reboot? Because that's the only way to.
Yeah, I mean that's not recover, right? I mean
right.
that's a catastrophic way to recover from stuff. So it's not considered recover. It's it's what you would like in a recover is some sort of a way to get back to a good state and make progress or something,
okay.
right? What you'll end up doing is kill the processes, and if you're using a printer, half your printout is done, then you tear up the paper, restart again, and hope that you won't get into the deadlock again, right? That's usually not an acceptable solution that you're looking for, but that's what you do. Right? Yes?
Are there any popular operating systems that do account for deadlock?
No. The reason why is the reason. So the usual logic is deadlock should happen. It should not happen often, right? There are two ways deadlocks can happen. One is in your application process, and one is within the kernel. If I look at the operating system perspective, if operating system is written well, deadlocks should not happen often, right? So if it's not going to happen often, why bother, right? If it happens at the user level, right, then you would kill the process. So if you, I mean, it's very easy for you to get into deadlock if you write a bad code, like the previous, two-wait situation, you'll get into deadlock. But as operating system, I don't really care what you get into, kind of stuff, right? The other reason is deadlock prevention and avoidance, it doesn't come free, right? Hopefully, when you look at the two graphs and all those things, it's clearer. It's not that easy to figure out that deadlock has happened or deadlock is going to happen, right? And it's not easy to figure out that you're in a complete starvation case or you're in a deadlock state. The only way you can make sure is, you have all these resources, you know who should use resources. So in the graph, we had resources and said there's two instances of the resources, and we said, it's mutual exclusion principle and all those things. Usually operating systems don't really care what the resources are, right? So now you have to add all this notion into the operating system and say, printer is a non, some resource kind of stuff. So if you put all the stuff, and every time you ask for a resource, you have to make sure that resources, deadlock cannot happen, right? And depending on how much guarantee you want, the system will actually cause starvation. We'll see some of what would happen when you try to do prevention, all those things, right? So if the more conservative you are, the more you want to make sure the deadlock never happens. That means I can't give you a resource that could possibly cause a deadlock, even though it doesn't happen, right? So very few users are willing to deal with a slow system because they want to prevent a deadlock situation, which happens rarely anyway, right? So that's the logic. So, so from the OS perspective, if you're seeing lots of deadlocks, then the OS is buggy, right? And you should fix the operating system, not have get into deadlock. It's not the answer you would like to look for, because the next few slides I'm going to talk about how you prevent deadlocks and how you avoid deadlocks and stuff. But the practicality is all of the techniques are make the system slow, right? They would not give you a resource if there's a possibility that you'll get into a circular wait state, and that may be good to talk about as a technique, but not good in terms of real system, because real systems will kind of get through and keep moving, right? Okay. So those are excellent questions. So one of the harder part is when I talk about prevention and stuff, real systems don't do that, right? So it seems like it's a waste to study about this thing that no system would use. It may not be done by the operating system, but that's something that application code which does locking and stuff would have to be aware of, right? The reason why I say operating systems don't do that is it happens very rarely, right? But in the application program, it'll happen a lot more, right? So that may be something that you would notice for your homework project too, right? If you're not careful, you can get into a deadlock situation very easily. And usually when it gets to a deadlock situation, all you know is nothing happens. You just sit there, and after a while you kill the process and go on, right? How many of you have faced deadlock situation in any code that you've done prior to this class, where your system, where your programs just stop? So what language are you using? C++? How did you get out of it? Kill it. Finding it whether deadlock happened even for human intervention is very hard. I don't know if you try to debug through and see what really happened, right? Because deadlock looks very similar to starvation, right? Just because your program is not printing something does not mean it gets into a deadlock. But from a practical perspective, they're both the same, right? You don't want infinite starvation too. So those are caveats, but let's go on to look at what would be required to implement deadlock prevention and avoidance, right? One of the other stuff which is not exactly in your book, right? The book talks, so you expect deadlocks to happen, say, once in some time, right? So once in, say, 6 months or a year, right? What is the typical rate that you reboot most of your normal systems, like your whatever operating system that you used, right? Windows or Mac or what have you, right? If it's not in terms of decades or centuries, right? These sort of things are, you probably never noticed it. You probably never noticed that your OS got into a deadlock, right? which is not the stuff you want to look at, but that's the reality of the commercial operating systems you look at. Mainframe operating systems don't operate in that model, right? So one of the anecdotal evidence I heard was IBM System 390. I don't know how many of you heard of this stuff. IBM 390 is their line of mainframes that IBM has been making since 1980 or so, right? It's a line of machines, so it's not exactly the same. So it's a series of machines. You can program them the same way. The hardware and everything keeps changing. So whatever you bought in 1980 is not the same that you're going to buy now. It may have different processors and things change, but it's the same machine, right? So sort of like your x86, it's the similar architecture which moves forward. So whatever program you wrote in 1980 for System 390 should still work now, right? And these are usually running in mainframes, banks and stuff. So the Bank of Tokyo has been running apparently one machine since 1990 or something, so like 15 years, right? So that means this operating system is running for the last 15 years on this machine, right? The notion of this machine is kind of vague because those machines let you upgrade stuff. You can upgrade everything, including CPU, right? So the OS is running for all this time, except whatever OS was running, whatever hardware it was running on day one, is not the one it's running right now. So you can replace the CPU, replace memory, replace IO processors and stuff. You probably keep the same rack or shell, but you keep replacing stuff, right? You upgrade operating systems, right? But you never shut it down. So because it's controlling the bank, right? So they cannot afford to bring down this machine, because if you bring down the machine, I don't know, like all the ATM machines will stop working or something like that, right? When you're building some things like that, you're extremely conservative, right? And I suspect that if you're building those kind of systems, you worry about deadlock prevention and stuff, because you don't really care about performance, you don't really care about speed. You want to make sure absolutely that nothing ever breaks. Right? From IBM perspective, they can tell customers, we've had the system running for the last 15 years since they bought it. Right? The machine has never been shut down. The OS has never been upgraded or what. So OS has been upgraded but never shut down, right? And for those kind of systems, you want to make sure all the stuff. But very few of us work on those kind of machines. Most of our machines, we reboot them so often, we don't really care whether it's deadlock or not. And I suspect that if you're writing operating system for those, it's a lot conservative, right? So one of the reasons why I knew about this is they were trying to install Java on those, right? So the time quanta that was assigned to System 390 back in 1980s was way too long, right? It was more of a batch processing system, so you can't reduce the time frequency to interactive processes, right? So people wanted to port Java onto this machine, right? And for your homework one, you just recompile it, change the clock, recompile it, reboot it, and it was fine, right? So it's very trivial to change that in the operating system. You just go change some variable somewhere, some constant somewhere, things work. So you could do the same thing on the OS on that particular machine to make it interactive, right? But it's not that easy because you could replace it, but you're not going to convince that bank or anybody to reboot the machine, right? So they actually had scheduled the upgrade to Java in 2015 or something like that, right? Some 10 or 15 years, right? Out, because stuff that we did for homework one, even though it's easy from our perspective, can't be implemented, right? But we don't usually talk about those because those are not the kind of stuff that most people tend to use. Right? Anyway, so let's get back to the deadlock prevention mechanism. Deadlock prevention tries to prevent deadlock. It does not guarantee that deadlock would never happen, right? So if you want to guarantee that deadlock will never happen, then every time you give a resource, you have to look at all the possible future moves and see that none of them would ever get you into a deadlock. And we'll see how those are done in the next section. For now, you try to make sure that deadlocks are unlikely, right? And that's the notion of a deadlock prevention. So you go back to look at all the 4 principles and make sure that you can avoid one of them, right? So the first principle is the mutual exclusion, and so mutual exclusion. So some of the resources are inherently have the mutual exclusion property, right? Like the example I was giving, the printer, right? Printer cannot be shared with anybody else while I'm printing, right? So if you use a printer, and if I have to hold the printer to make a printout, then I cannot do anything about it, right? So can you think of a way where I can avoid, where I can get mutual exclusion principle away from a printer? How would you? A resource like a printer cannot be shared by 2 processors at the same time. What's a possible way where you can make this less of a problem? You've used it all the time, so yeah.
You could spool the jobs so that, it appears to the thread that wants it that it has printed, whereas the printer just sort of stores it in memory and then prints it at a later time.
Yes, exactly. So basically spool the thing, right? When you use a program, you rarely print directly to the printer. So you have a program, your print spooler or what have you, which collects all the printing jobs and then sends it out after it's all done, right? So it makes it into a transaction essentially, right? So when you start a printout, you go for the whole thing. Once you're done, you make it into a transaction, then you give it to the printer. It's not really transaction because it could still fail halfway through, right? You're kind of moving the failure modes to a different stuff, right? So if you were doing it on a mutual exclusion, if you're doing it the real way that printer would have been, right? If a printer runs out of paper halfway through your process, then your program would have stopped. But if you're using a spool model, then those errors cannot be recovered from, right? So for normal processing, just making the printer spooled would break the mutual exclusion policy for the printer, so you can make progress, right? And it works for most of the cases, except cases like what I mentioned. So the cases where that will happen is something like if you're a bank and you want to print your check, the cashier's check or whatever, right? Those, if it fails, then the system has to recover from it. It's not something that you can resend it and stuff. So there are ways OSs can make some of the resources avoid the mutual exclusion. Most operating systems typically tend to use that. The other way is the second principle we said was hold and wait. So if I hold the resources and then I have to wait for another resource, right? For deadlock to happen, I should be holding some resource and I should be asking for new resource. So if you want to prevent deadlocks, you can either force the application from not holding resources, right? So you can do this sort of like, you can only request resources and then return them, but not go through the same, in interleave fashion. So some of the ways you can do that is before you start the process, you have to ask for all the resources that you want, and then you can proceed, right? Or if you have to wait, I will take away all the resources from you, right? And before you can restart, you have to require all the resources, right? So if I have resource 1 and 2, and I need 3, right? When I wait, I give up my 1 and 2, right? And then I have to now wait for all 1, 2, and 3 to be made available before I can make progress, right? So that would make sure that deadlocks are unlikely. That will also make for a very slow system, and that's one of the reasons why you don't try to do those, right? So I may have 1 and 2, now I have to give it back and I have to ask for this again, right? So if I have a resource which is very popular, then I would rarely get those, right? So now I'm replacing what I have with the AND operator, right? If I have 2 very popular resources, then any process which waits for that and the other popular resource would never make progress. So yes, you prevent deadlock, but your system would be terribly slow for popular resources. But those are certain things you can do. The other stuff about asking all the resources before you start is easier said than done. So you have to change your program to essentially ask for all the resources upfront, and that means you have to change the program, not something that the OS can demand, right? Most of the time when you write a program, when you need something, you ask for it. When you need a printer, you open a printer. You don't usually say, before I start the program, before my main in C starts, I need to have all these resources, right? It's incredibly wasteful, and you have to change the way you do the program, right? So you can also prevent the, so you can go back to the next one, which is the preventing the preemption policy, right? So if there's no preemption, then you'll get into deadlock. So you can force that to make the illusion of a preemption, and so when you're holding resource, you can forcefully preempt what you have and then bring it back. So sort of like CPU would go through this policy, right? When you have a CPU, when you are waiting for something, if CPU is taken away and given to somebody else, because CPU is a resource which is not preemptible, but you can make it preemptible by saving the state and restoring the state. Again, some of the like printers and stuff, it won't work. The last one is this circular wait, right? You want to prevent circular wait, and you can solve that by forcing some order. You can call resources arbitrarily by some number and say you can only request the next higher number than what you have, not go back, right? So if you wanted resource 1, 2, 4, and 0, right? You have to make requests as 0, 1, 2, 4, not 1, 2, 4, 0, right? You cannot. So you sort of prevent deadlock by forcing you to always request a higher number, forcing essentially the program to ask in a certain order, and that will prevent deadlock, right? So it's not important how you number these things. It's just important that they should move in a certain angle. And again, this leads to starvation, because now I have to hold a resource which I don't really need, right? So if you suppose you call the printer as the resource 0, right? I have to get the printer first before I start, even though I may run the program for 2 days and then start printing, right? You've now forced me to ask for the resources in a certain order, and that means that I need to get the resource that I probably won't need for a while, but I have to hold on to it and then use it, right? So these are some of the, so each of the solution would work, but they all lead to less resource utilization. So if it's not a problem, then you would try to do many of those. So the easiest thing you do is to do like things like spool. So things which are exclusive, but which can be spooled, you use that in an operating system. And things which can be like preempted, like your CPU and stuff, you do that. But you rarely do stuff like the preventing circular waits and other policies, right? So again, it's a notion of what performance gains do you want to give up for doing the deadlock processing, right? So we kind of a little ahead on from the schedule in the book, right? So the deadlock prevention tries to prevent you from doing some other stuff. It does not fully solve all the problems, right? So for example, if you have a resource which cannot be preempted, which has all the things we talked about, then you cannot solve the first 3 issues. So if you're trying to print to a direct printer, it cannot be preempted, and so on. So deadlock could happen if you cannot do all of those. So there are some resources which would fall into that category. So the notion of deadlock avoidance is, before you allocate resources, you make sure that there is no possibility that anything in the system will ever get into a deadlock, right? Which is a lot stronger than what you were trying to do, because there we are trying to do little hacks which pushes the problem further out, right? So we basically made the printer and put a spooler on it to make it less likely that, so except for applications which need to print directly to the printer, right? You made the printer not a deadlock, part of the deadlock for a whole bunch of applications, but you didn't prevent the system from ever having a deadlock, right? So if you want to do deadlock avoidance, you want to make sure that before every resource, you have to run through all the system. You have to see all the resources which are allocated to all the processes. Essentially, try to look at the resource allocation graph to see that if I give this resource to another process, is there ever a possibility of getting into a deadlock? Right? And you know, the way I said it, it's kind of clear that that's pretty complicated, right? So before I can give a resource, I need to run through the whole thing. But there are classical solutions to this problem, and that's why we try to look at how you would do that. So most of these require that you know the future. Most of these require that we have to figure out what resources you have, all those things. So one easy way to help this is for the processes to say all the resources that it would ever want. So when a process comes in, the system can figure out all the resources that you want, all the resources that are allocated to the different processes, so it knows whether you can get into a deadlock, right? So in this notion, you cannot ever get into a deadlock. So you're trying to make sure the deadlock will never happen, right? So if you have a process which actually asks for 1 and 2, and if it asks for resource 3, then you get into a deadlock, right? If the OS does not know about it, then you're in trouble, right? The process can, you admitted the process. In the future, it may ask for a resource which will cause a deadlock. So the simplest way to deal with that is to say all processes have to declare all the stuff that they want upfront. So when you ask for all the resources, you try to figure out if there's ever a possibility that given the resources that you want and given the resources which are allocated, if you'll ever get into deadlock, right? And you will be extremely pessimistic because the applications may never actually do anything bad, right? So the application will say, I may want a printer, I may want a disk drive, I may want a whole bunch of stuff, but in reality, it may never use any of those, right? Because error happens or whatever, but it has to ask for everything that it wants, and you run this program to see if there's ever a possibility of anything getting into deadlock, even though there is realistically no condition, right? So the other way is to try to do this dynamically, right? Not upfront, but trying to figure out based on what resources you have and what you're asking for, whether you will run into a deadlock, and if you go run into deadlock, deny that particular request, right? And most of the cases, if you deny halfway through, the system is going to be very few times can you recover from those, right? So it's going to behave similar to what happens when you run into a deadlock situation where you have to kill the process, right? So if at this point, if I want a printer to get my output out, and I ask for a printer, and if the OS says, I can't give you because if I give you a printer, then the system can possibly get into a deadlock, right? You prevent the deadlock, you avoid the deadlock, but this process, there's nothing else. I mean, usually the process will have to kill itself because it can't make progress, right? So even though you solve one problem, that necessarily may not mean that the application itself is happy about it, right? So I'm going to stop with this state because with this slide and continue with the next one. And basically, we have to define different states in the system, right? Basically, we're trying to define states where we know deadlock can never happen, and we'll define states where deadlock may happen and the states where deadlock will happen, and how you try to stay in safe state all the time. Whereas in prevention, you would try to go to a state where it could be unsafe, but you still try to make progress. Right? We continue with that on Monday.